Welcome back. In the second part of this lecture, we're now going to apply our knowledge of the luminosity of stars and the temperatures of stars to introduce the Hertzsprung-Russell diagram. The Hertzsprung-Russell diagram is a plot of the luminosity versus the temperature of stars. We get the luminosity from measuring the apparent brightnesses and distances of stars, distances in this case usually through stellar parallaxes. And we get the temperatures of stars by measuring either their photometric colors or their spectral types, OBA, FG, KM, following the Harvard classification system developed by Pickering and Fleming and brought to its highest level of development by the work of Annie Jump Cannon. Two astronomers, Einar Hertzsprung from Denmark and Henry Norris Russell in the United States, both independently made the first of the plot of luminosity versus temperature that now bears their name, the Hertzsprung-Russell diagram. Einar Hertzsprung was using data for star clusters, groups of stars that are all at the same distances, so differences in their apparent brightnesses represent differences in their absolute luminosities. Whereas Henry Norris Russell was using data for nearby stars for which he had reasonably good parallax distances and therefore could compute their luminosity from their apparent brightness and parallax distances. Both of them used temperatures derived from spectral typing done by Cannon and others at Harvard. On the left, we show the first original HR diagram, for short, Hertzsprung-Russell, plotted by Henry Norris Russell in his famous 1912 paper. The y-axis, the vertical axis on this plot, shows a representation of the absolute luminosity in what's known to astronomers as an absolute visual magnitude. This is just a logarithmic way of representing luminosity with a straightforward observable. We're not going to go into the details of how it works, just know that a large number at the top and a large negative number, somewhat unintuitively, is high luminosity and low luminosity at the bottom. The horizontal axis uses the spectral classification found by Cannon and others for stars for which Henry Norris Russell had parallaxes. Because there are no nearby O stars or near enough to have gotten parallaxes at the time of Russell, we don't see any O stars on the left-hand side of the diagram, but he begins with type B, then A, F, G, K, and M, and he's still using one of the classes N that had survived in the early part of the 20th century but is now gone. They're now recognized as being very, very cool M stars. And so this horizontal axis is also kind of backwards. It runs in temperature from the hottest stars on the left to the coolest stars on the right. This is a state-of-the-art Hertzsprung-Russell diagram from 1912. This is a state-of-the-art Hertzsprung-Russell diagram from 1915. This is using stars that were measured using the Hipparcos satellite that measured not only parallaxes, as we saw in a previous lecture, but also measured precision photometry for the stars. The precision photometry was done in blue and red filters, which instead of using a spectral color, develops a color index. A color index is basically the difference between the ratio of the amount of blue light to the amount of red light seen in a blue filter and a red filter, which is then represented on a logarithmic scale and becomes a stand-in for temperature, hot on the left, blue on the right. The vertical scale is using the same absolute visual magnitude, this proxy for luminosity, that would be familiar from Russell's day. And I've scaled both of these plots so they are on exactly the same scale. We can see the same basic features in Russell's original diagram from 1912 in this version, which contains data for many thousands of stars, all within 100 parsecs of the Sun. It's this diagram on the right that we're going to be using for most of our discussion in this and subsequent lectures. Let's take a closer look at it by expanding it out. Now I've replaced the somewhat technical absolute visual magnitude, converting it into the luminosity of the star in units of the luminosity of the Sun. The first thing you'll notice is the extremely large range, from 1/10,000th of the luminosity of our Sun to about 250,000 times the luminosity of the Sun. And that's not really the upper end. The most luminous stars in our galaxy can be upwards of 1 million to almost 10 million times the luminosity of our Sun. Because of the enormous range from 1/10,000th to 250,000, I've plotted this on a logarithmic scale where each major tick represents a factor of 10. On the horizontal axis, I've plotted a spectrophotometric color index, which ranges from a negative number for the bluest stars and a large positive number up around 2 for the very reddest stars. And to clue in the eye, I've color-coded each of the data points by an approximate representation of their naked eye color, exaggerated to make the bluest end bluer and the reddest end redder. In this diagram, think of it as stars go from blue on the left to red on the right, which is running from hotter to cooler stars in a smooth progression. The temperatures here are about 50 to 60,000 degrees Kelvin on the left, down to about 3,000 degrees Kelvin among the coolest stars on the right. The luminosity scale runs from dimmer stars, stars that are less luminous than the Sun, to brighter stars, stars that are much, much brighter, much more luminous than the Sun. Remember that luminosity is a representation, a measurement of the total amount of energy per second pouring off of a star. It's a very important physical quantity. The horizontal axis represents the stellar photosphere temperature from hotter to cooler, but when we're plotting an observed Hertzsprung-Russell diagram like this, we will almost always express this as a color index because that's the direct, simple observable. This can be translated into temperature, and indeed when we talk about theoretical Hertzsprung-Russell diagrams developed from stellar structure and evolution theory, we will often replace color index by temperature. Get used to these changes. We're going to be seeing the HR diagram a lot because it is going to turn out to be one of the most important tools we have for understanding stellar structure and evolution. And we're going to be looking at a lot of these over the next few lectures. Now, if you look at this diagram, you will notice that there's one key insight we can gain right away. Stars do not have just any old combination of luminosity and temperature. Stars are not evenly distributed across the Hertzsprung-Russell diagram. Indeed, stars very strongly clump and cluster into very specific loci across this diagram. We can see this broad horizontal band running from hot, high luminosity stars all the way down to cool, low luminosity dim stars. We see a very strong clump of stars that tend to be red, but very, very luminous, and a scattering of stars at a whole range of temperatures, but sometimes to extremely high luminosities. And then sitting down here kind of all by themselves are stars that are very hot and very blue, but very, very dim. They're very low luminosity, luminosities of only a few thousandths to a few tens of thousandths of the luminosity of the Sun. These patterns are trying to tell us something important, and indeed, understanding these patterns was the key to unlocking the secret of stellar structure and evolution. Let's start in and looking at some of these patterns. We're going to be doing this empirically, but later we're going to describe what's going on. The first thing we'll notice is that nearly 85% of nearby stars lie along a distinctive diagonal band that is referred to by astronomers as the main sequence. It's called the main sequence because it's the primary sequence of luminosity and color, or luminosity and temperature, that we see among stars. Stars along the main sequence are, if they're hot, they're high luminosity, and if they're cool, they're low luminosity, and everything in between along this approximate diagonal band. The basic properties of main sequence stars is they have a very large range of luminosity, more than a factor of 10 billion in luminosity, from 1/10,000th of the luminosity of the Sun to more than 1 million times the luminosity of the Sun. Those same stars have a relatively narrow range of temperatures between 3,000 degrees Kelvin and about 50,000 degrees Kelvin, only about a factor of 20 in temperature. And they have a range of approximately 1,000 in radius, from 1/10 the radius of the Sun to the smallest stars, to about 10 times larger than the Sun for the very largest radius stars. The other important takeaway fact for today is that the Sun, is a main sequence star. Here is the Sun sitting right here at 1 solar luminosity, smack dab in the middle of the main sequence of nearby stars. The nature of the main sequence and why physically 85% of stars nearby are on the main sequence will be much of the subject of a subsequent lecture. Today we're just going to concern ourselves with basic descriptions. Remember our usual progression of knowledge. First you describe it and characterize it, and then move on to understanding why does it have these properties and understand it physically. Remember the luminosity radius temperature relationship for stars. If two stars have the same temperature but different radii, the larger star will be the more luminous. As you'll recall, if we have two stars, A and B, both of which have 6,000 degree Kelvin temperature on their photospheres, but star B is 2 times larger than star A, then we know through the luminosity radius temperature relationship that the ratio of their luminosities should scale like their radius and temperatures, radius squared and temperature to the 4th power. Because these two stars have the same temperature, the 4 pi and the temperatures cancel, and the luminosity of two stars of the same temperature will scale like their ratio of their radii squared. Since star B is 2 times star A, that will be the ratio of 2 to 1 squared, which is 2 squared or 4. And so if star A and star B have the same temperature, but star B is 2 times larger than star A, then star B will be 4 times, 2 squared times, more luminous. Why have we reviewed this in detail? Because of a very distinctive pattern that appears on the Hertzsprung-Russell diagram. Stars that are much brighter than main sequence stars of the same temperature must have larger radii. The luminosity radius temperature relation tells us if two stars have the same temperature, but one star is more luminous than the other, the more luminous star has the larger radius. We recognize two basic loci of these stars on the HR diagram. The first of these groups are somewhat suggestively called the giant stars. These have luminosities between about 10 and 10,000 times the luminosity of the Sun at their most luminous, and will have radii between 10 and 100 times the radius of the Sun. For example, consider a red main sequence star down on this little knee here on the main sequence at about 4 hundredths of the luminosity of the Sun. They have the same temperature as stars up in this group, but this star has a temperature of luminosity of 10, 20, 30, 40, 50, 60 times the luminosity of the Sun. So we've gone from 4 hundredths the luminosity of the Sun to 60 times the luminosity of the Sun, but at the same temperature. And so they must have a much larger radius. And we call these stars, somewhat suggestively, giant stars because they are truly giant in radius. Are they giant in mass? We don't know yet, but we'll learn in subsequent lectures. But the giants aren't the biggest thing out there. These stars over here have the same temperature as these giants, but they have even higher luminosities, up to almost 100,000 times the luminosity of the Sun. But they're much rarer. There's just a thin spattering of them. Some of them are blue, some of them are red. These that we classify at the very top of the Hertzsprung-Russell diagram, at the highest luminosities and range of color, but off the blue end of the main sequence, are called the supergiants. The supergiants range in luminosity from 10,000 to 1,000,000 times the luminosity of the Sun, and can have radii of 1,000 times the radius of the Sun and up. How big is that radius? So big that some of these supergiant red stars, if placed in our solar system, would fill our solar system all the way out to the orbit of Jupiter. So the giants and supergiants are stars that by dint of being the same temperature of main sequence stars but vastly more luminous, we immediately know from the luminosity radius temperature relationship they are larger in radii. Not necessarily larger in mass, larger in radii, as we'll see. Stars that are much fainter than main sequence stars of the same temperature must have smaller radii. This is turning the problem around. Well, notice down here on the lower left-hand corner of the HR diagram are stars that are very hot but very low luminosity. They're vastly lower luminosity than main sequence stars of temperatures of 30, 20, 10,000 degrees Kelvin. These stars down here have luminosities of a 10,000th to a 100th the luminosity of the Sun, whereas these hot blue stars are 20, 30 times the luminosity of the Sun, up to 10,000, nearly 100,000 times the luminosity of the Sun. We know these stars must be really tiny. How tiny? They're only about 1/100th the radius of the Sun. That's the radius of the Earth. And yet, as we're going to see, they have masses between 0.4 and 1.4 times the mass of the Sun. These are pretty amazing stars. These white dwarfs turn out to be very, very unusual objects, as we're going to learn later in this course. So here once again is our Hertzsprung-Russell diagram. I've replotted it, and now I've called out some familiar stars by name and plotted them on the HR diagram in their correct locations for their temperature and luminosity. Temperature, I'm using the stand-in of color index, but now I've drawn the size of the circle in the approximate scale with respect to the Sun. The Sun here, it's a G-type star, and we call it a dwarf star. Stars along the main sequence are often referred to as dwarf stars. Sirius and Vega, two of the bright blue stars in the sky. Sirius, the dog star, is the brightest star in the sky. These are A stars. But they're on the main sequence, and so we call them A dwarfs. Proxima Centauri, the nearest star to the Sun, is this little tiny, teeny, faint star, red star, down here on the lower right-hand corner of the HR diagram. It's a spectral type M star, but it's tiny and cool and is referred to as an M dwarf, or often because of its visible color, we refer to them as red dwarfs. Aldebaran, the bright red star in the constellation of Taurus, the bull in this winter sky, almost forgot it there for a second, is a red giant star. It's a K-type star. It has a slightly reddish appearance, and indeed, if you look carefully at Aldebaran in the nighttime sky, it does have a slightly reddish appearance. Rigel, the bright blue star in the constellation of Orion in the winter sky, is an example of a B-type blue supergiant star. It's not on the main sequence anymore. It's just a little bit to one right-hand side, and it's more than 100,000 times the luminosity of the Sun and very hot. Finally, Betelgeuse, the bright red star also in the constellation of Orion in the winter sky, is an example of an M-type supergiant. It's an M star, very cool, spectral type M, but its luminosity is a few thousand times the luminosity of the Sun. I've drawn these in their various scales, but I've had to cheat a little bit. The relative sizes are not exactly correct. I had to do this in order to fit them onto the HR diagram without obscuring them. Finally, Sirius B, a white dwarf, is the binary companion of Sirius, the A dwarf, is in fact one of the nearest examples and brightest examples of a white dwarf star. Lies down here on the white dwarf sequence on the HR diagram. If I now replotted these stars with their relative radii scale, not on a logarithmic scale, but on a linear physical scale, we can see the tremendous range of radii of these stars. We start up here with the Sun, which has a radius of 1 R Sun, and I've drawn it with its approximate spectral color. This is going to be my reference. Sirius, the dog star, the brightest star in the winter sky, is about 1.7 times the radius of the Sun, but it's much hotter than the Sun. It's got a temperature of about 10,000 degrees Kelvin, which is, in round numbers, about 2 times hotter than the Sun. But remember, the luminosity radius temperature relationship is that luminosity scales like radius squared and temperature to the 4th. So 2 squared is 16, so there's at least 16 times more luminous than the Sun just due to its temperature. It's another factor of 1.7. Call it 2 in round numbers, but 2 squared. So 4 times 16 will tell you that the luminosity of Sirius is getting up around 50-60 times the luminosity of the Sun. It is both larger in radius and hotter in temperature. Vega, the brightest star in the summer sky as seen from the north, is about 2 times the radius of the Sun and also a temperature of about 10,000 degrees Kelvin. Aldebaran, the bright red star in the constellation of Taurus the Bull, is a red giant. It is 44 times the radius of the Sun, but it's cooler and appears red. Rigel, the blue supergiant star in the constellation of Orion, is a hot blue star with a radius of 80 times the radius of the Sun, and we can see it here is in fact a circle drawn 80 times bigger than this little circle here. But Betelgeuse, the red supergiant in the constellation of Orion, is really big. I simply can't draw it to scale. You should just be able to tell there's a slight faint curvature from one side to the top and bottom of the screen here. Betelgeuse is enormous. Again, if we took Betelgeuse and plopped it down on our solar system, it would consume the entire inner solar system and asteroids all the way out to the orbit of Jupiter. They really are supergiant stars. But here's the thing. It's supergiant in radius, in size. That does not necessarily mean supergiant in mass, as we're going to learn later. The Hertzsprung-Russell diagram is extremely important to astronomy. It's, as I've said many times before, it is the key to understanding the nature of stellar structure and evolution. And indeed, we're going to be using Hertzsprung-Russell diagrams over and over again through this course because they give us so many keen insights into what is going on. The existence of a Hertzsprung-Russell diagram, the fact that stars do not just have any old luminosity and temperature, raises many questions. The first is the most obvious. Why is it that stars don't have just any combination of luminosity and temperature they want? Why are there particular places on the HR diagram where stars reside? Why is it that on the main sequence, the hottest stars are also the most luminous, and the coolest stars are the least luminous and dimmest? It isn't obvious without a deeper understanding of stellar structure. Why is there a distinct main sequence? Why is there that diagonal band? And why is it that when I look at stars around me, 85% of them are on it? What's special about the main sequence? How does that work? What makes one main sequence star different from another? Why is the Sun where it is on the main sequence? Is it just a difference of luminosity and temperature and radius? Or is there something more fundamental at work? It isn't obvious from looking at the diagram. We're going to have to dig deeper. Were giants, supergiants, and white dwarfs all born that way? Did they end up on the diagram because, well, they're kind of like Lady Gaga. They're just born that way. Or is something else going on here? Did they born there? Or did they get there somehow and start out somewhere else? And if a star is a main sequence star, or a giant, or a supergiant, or white dwarf, do they always stay that way? Or do they move around the diagram? Do they change their luminosity and temperature as they age? All these patterns on the HR diagram are giving us very important insights into the structure and evolution of stars. And indeed, much of the story that we're going to be spinning out over the next few lectures is going to be answering these and many more questions raised by what's a seemingly simple observational question. What are the luminosity and temperatures of nearby stars? Had a very interesting and profound answer that leads us into the secrets of stars.